Hello, welcome back. Today is lecture 56 and we are in the middle of discussing about passive components on an RF circuit. If you recall, in the last lecture we had introduced about the metal lines and also about microstrips and coplanar waveguides, which are very critical for not only enabling on wafer measurement, but also they are very critical or indispensable for instance MMICs. You have to have these microstrip lines for so many reasons, such as impedance matching. You can mimic a capacitor or an inductor using a transmission line. For instance, a transmission line can be implemented using a coplanar waveguide or a microstrip or a strip line. Okay, we are talking about that. And then we are moving about into inductors. Okay, so we have to go and discuss about some of these very important passive components, such as an inductor, a capacitor, a transformer, etc. Okay, so we are going to do that step by step today. So to the whiteboard here, I'll just recap some of our discussion on the inductor again. You need an on-chip inductor, correct? If you want to talk about passives on the chip, on the wafer, then we are not going to buy an inductor from the market and put it there, by integrating. It's just fabricated on the wafer, for instance in an MMIC. Okay, you have to fabricate everything on the wafer on the same die, okay, using the fabrication processes. So the way people implement inductors is typically using a spiral. There are other ways also, but a spiral inductor is very common. So you can see on the left it's a square, on the right it's a circle. Designers will decide which one to choose depending on the values of inductor that you need, how much nanohenry for instance you are going to aim for, what kind of Q factor you want. Q factor is a quality factor. It's a very important parameter. It will tell you how well your inductor is behaving as an inductor and not like a capacitor, for instance. Okay, because with higher frequencies your inductor will tend to start behaving like a capacitor. Okay, so the value of inductance in terms of how much nanohenry you need, the quality factor, what is the value of quality factor you need for the circuit, what's the bandwidth, okay, the frequency over which you are going to operate the inductor. Okay, so all these things will matter and the designer will choose what kind of inductor configuration or topology he or she chooses. Okay, so the spiral inductor is a very widely used topology, and you have to note that inductors can be very large. Because you need very large values of inductances, then your inductor will also occupy a large area or a real estate on the wafer. So inductors are very large, so the goal has always been to try to get as much inductance per unit area as possible, so that you can have a smaller area and still get the same value of inductance. Okay, so typically inductances of values from 10 nanohenry to 0.1 nanohenry can easily span a frequency of 5 to 50 gigahertz, as I have written in the slide also. So for this range of frequencies, that kind of inductance values are what are desired. Okay, an inductor has something called a self resonance frequency, SRF. That is the frequency beyond which the inductor is no longer an inductor, it is a capacitor. So it is the maximum frequency at which your inductor will be an inductor. Okay, then there is of course the operation range. Just because you have a certain self resonance frequency doesn't mean you are going to operate near that point, because your Q factor will be horrible there. So you need to have an operation range where you are going to use the inductor. Now before that, the fundamental key thing about inductor is that it stores magnetic energy, that we know from high school physics. Okay, and in typically we talk about like you have some kind of a rod or some kind of a pin there, and then you have this spirals that are winding up, and any change in magnetic flux will store magnetic energy. This is from high school physics that we usually visualize the inductor. Here on chip, of course, any metal line will behave as an inductor. The thing is that there is a ground plane below. You have to remember that there is a ground plane below. There's on the bottom there is a ground plane, and the top there is the signal. So this inductor is on the top of the wafer or in between some dielectric, but it is you can consider that there is a ground plane at the bottom, and then there is an inductor line on the top. So there is always going to be electromagnetic coupling, inductive as well as capacitive, depending on the frequency which one dominates. So there is always going to be, because it's RF signal, so you will always have an oscillating electric and magnetic field. So the magnetic field will lead to an inductance in this kind of a metallic line. You can have a simple straight metallic line, okay, without any spiral, and that will also be an inductor because there is a ground plane. So there will be magnetic or inductive coupling, and you will get you will be able to store magnetic energy in that line. So your metal line is also an inductor. The wire that you use for wire bonding the device is also an inductor. Okay, so everything, all the metal lines are inductor. However, the reason they give a spiral is because they want to increase the inductance per unit area. You want to get more value of inductance for a given real estate on the wafer. Okay. If you use a straight line like that, then you need a very large long straight line to get for instance a certain value of inductance, some maybe 10 nanohenry or whatever. But if you make a spiral, then you will condense that into a smaller area, you will have spiral, and then you will be able to have a smaller footprint of the inductor. That is the reason. And you have to understand that when the current flows, for instance the current may flow like that, correct, the current may flow like that. So what is happening is that there is something called constructive coupling. So all the current that is flowing in nearby lines, they are flowing in the same direction. So they have a constructive coupling. It enhances or reinforces the inductance value. So that benefit is lost out in a single long transmission line or a wire. You do not get the benefit of constructive coupling that you get. Okay. However, the current here flows this way and the current here flows that way. So they are opposite. So this and this will have a destructive coupling effect, but they are far away, so you tend to ignore them, but they can become important with higher frequencies and with smaller areas. So then again that is a trade off that you have to make, but typically these are much closer to each other. So the constructive coupling is stronger. Okay. And you try to avoid the destructive coupling as much. So that is the reason why you have this spiral. You try to maximize the inductance per unit area. You try to get the best out of a given real estate or footprint that you have. Okay, that is the reason. Otherwise you can have a straight simple line also, not a problem. Okay, that is your inductor, and there are analytical expressions that will give you the value of the inductor in an analytical expression, taking all kinds of fringing or whatever into effect in terms of the dimension. For instance, this is W, the spacing is S, and all the things. So that helps you understand or model the inductor. But nowadays there are more advanced tools such as ADS. Again, when I mention a tool from a certain company, I am not recommending or advertising for it, but I am just saying that there is a very widely used tool, for instance ADS software, and that is used by people to model the inductor. And then once you fabricate the inductor on the wafer, you can characterize it, you can extract all the S parameters, and then you can compare with the model. You improve the model iteratively, you go back, and that is how you characterize as well as model inductor and other passives as well as capacitors, transformers, etc. So modeling and characterization of the passives have to go hand in hand in order to have this robust platform of passives. Okay, so this is inductor, but there are many things of inductor. I will come to that one by one. So an equivalent circuit of inductor is shown here. Ls is the desired inductance value of the inductor that we are talking about. For instance, in the previous slide, for instance, if I look at this inductor, spiral inductor, then the value of the inductance that I desire is basically captured by this value Ls. What does Rs do? It is basically representative of the series resistance of the metal. The metal, it is always metal, of course, right, and the metal will have its own series resistance. So you include that effect as Rs. What is Cs? And that is in parallel, by the way. The metal resistance is in series with the inductance that you desire, but the Cs, the capacitance or the capacitive coupling, is in parallel to this series combination, and Cs captures basically the capacitance between the spiral lines. Okay. So for instance, between the spiral lines you might have some capacitances. It also captures the capacitance between spiral line and the underpass. What is the underpass? This is the underpass, you see, this is the underpass. You cannot have metallic short between the two lines that are crisscrossing over each other or here. So you need to design that fabrication such that one end of this line is going below the other end and they are separated by dielectric, such as a silicon nitride, for instance. Okay. So there is a dielectric that is separating the two. The fabrication process, the process flow has to be designed such that you enable that. Okay. It has to be thoroughly qualified, optimized. You cannot arbitrarily use a process. So there have all has process modules and unit process steps also have to be there, and the foundry will take care of that basically. Okay. So you need to have that underpass, and because there is an underpass, or you can say there are two metal lines crisscrossing on top of each other, or top and against, which have dielectric in between, you are going to get some capacitive coupling, which is also captured by this value Cs here. Okay. And then of course you have the oxide capacitance if you talk about a CMOS process, because there is silicon dioxide with which you couple to the substrate. The substrate is modeled by a substrate resistance and a substrate capacitance, because oftentimes in CMOS your silicon, although it can be high resistive, it is not technically high resistive at RF frequencies, it is quite lossy. So the substrate, the silicon substrate is modeled by a lossy network. It is a substrate resistance is in parallel or in shunt with substrate capacitances. Both are non-negligible because silicon substrate is leaky or lossy at RF frequencies. But if you consider a 3-5 semiconductor such as maybe gallium arsenide or gallium nitride, then COX does not exist because there is no dielectric oxide per se, and the substrate losses could be also much lower than what you get in silicon. Okay. But this is an equivalent circuit of an inductor. And the interesting thing here is that with larger inductor footprint or area, of course you get a higher inductance value, that is very obvious, but you tend to also sacrifice your self resonance frequency. The maximum frequency at which you are going to operate will also will take a hit, or it will reduce when you go for large and large area inductors in order to get to large and large inductance values. Okay. Now when you have a larger metallic area or footprint, you also increase the capacitive coupling to the substrate, and so your inductor will now start behaving as a capacitor at a lower frequency. That is why your self resonance frequency will reduce. I will show you plots of all of this, so it will become even clearer as we go ahead in the lecture. Okay. Now Q factor is very important, as I discussed already in the last lecture, but I am just repeating because these are very critical as we talk about passives. These are important parameters that you have to really digest and understand and internalize. Q factor is the ratio of the desired quantity by the undesired quantity, simple. Different components will have different definitions of Q factor based on this. The fundamental definition is the same, which is desired versus divided by undesired, and so you want the Q factor to be as high as possible, you want the undesired quantity or the denominator to be as low as possible, okay, and the desired quantity to be as high as possible. So for a resonator the Q factor could be defined differently, for an inductor the Q factor would be defined differently when you talk about the actual details. Okay. In case of inductor, it is basically your inductance, right. So you want the inductive component to be much larger than the parasitic resistive component or maybe the capacitive component. You want the resistive component and the capacitive components to be as minimum as possible, you cannot avoid them by the way, and you want the inductive component to be as high as possible for the metal line or for the spiral inductor. Okay. So this Q factor you want to be as high as possible. I will show you what typical values are there in the state of the art devices and all, but it is a product of 3 factors 1, 2 and 3. Okay. So what does, maybe I can just take a white screen here. The Q factor has 3 dependents. One of them is your QLF. What does this mean? What does QLF mean? It is basically your, it's your low, LF stands for low frequency, so it's your low frequency limitation on the QF, and it is determined by the losses. It's typically the metal line losses, the metal losses that are happening, it's the resistive losses that are happening. Okay. Those are at low frequencies, they are predominant, and that is represented by QLF. Okay. And then you have this substrate loss KSL, this represents the substrate loss. Now for a compound semiconductor such as gallium arsenide or gallium nitride, this could be very negligible. When I say negligible, it could be almost close to 1. If it is close to 1, then it does not, it cannot be more than 1. This loss factor is 1, in which case your Q does not get affected by this, but for a CMOS process for instance, this could be lower. You know, you have significant substrate coupling that is happening, or you can say you have a significant substrate loss that is happening, and it could be say 0.6. In that case your Q factor is reduced to 60% of what you would otherwise get, right. And then of course you have KSR. Okay. This is the third component, which basically represents the self resonance factor. You know, the self resonance factor essentially it sets the upper limit of the frequency on which you are going to you are going to get an inductive behavior for an inductor. Beyond that it will become like a capacitor. Okay. So those 3 factors at the self resonance frequency, this will become 0. That means your Q factor will become 0 at your self resonance frequency. So now I see that if I am going to plot the Q factor of an inductor as a function of frequency, then at certain frequency, say this frequency self resonance frequency, maybe say 10 gigahertz or 100 gigahertz whatever, the Q factor will drop to 0. This is 0, the Q factor will drop to 0, but as I lower the frequency, the Q factor will keep increasing, because as I am increasing the frequency the substrate coupling is increasing, and this is the limit. Beyond this part the Q factor, you know, it's meaningless, it's there lower than 0, it is becoming a capacitor, not an inductor. Okay. So your behavior as an inductor is only limited till this point, beyond that it is capacitor. So lower the frequency you come, better is the Q factor, until it reaches a peak and it falls off. This part is basically the low frequency part, where the metal resistive lines are playing a role. So in a way, if you are increasing the frequency at the lower frequency regime, you can think of, you can ignore the capacitive coupling, you can just think of the impedance as R plus JL, so J omega L. So the predominant, you can say that at low in this frequency range the resistance is fairly constant. So as you are increasing the frequency omega, this component also increases as your omega increases, correct. As your frequency increases, this component increases, and that is good thing because it is an inductor, it is supposed to behave like an inductor. So it's a good thing, as you are increasing the frequency, your Q factor is also increasing because it's in a way proportional to j omega L by R. So your j omega L is increasing because your omega is increasing, so your Q factor is improving. At beyond at one point your capacitive component will start playing a role. You will have substrate coupling, and that will reduce your frequency and it will eventually hit the 0, and that is it. So your sweet spot is basically around the peak frequency range, So this would be your desired or sweet spot where you are going to operate your inductor. This is the regime where your inductor behaves the most like an inductor. It is the more efficient, is the most efficient energy, magnetic energy storage in this frequency range. Okay, so that's what it means. But anyways, I just wanted to mention that. Now this is the plot of inductance. You can see this is on the y axis is inductance, on the x axis is frequency. You can see that your inductance value is basically your Q factor value is this. Maybe I can use the red here. Okay, this is your inductance value, this is the Q value, sorry. The Q value is on the right hand side, by the way, this is on this side. So the Q value goes like this, it is a peak and then it comes down. You can see this is the 0, right. So this is your self resonant frequency, which is close to maybe 5 gigahertz. So 5 gigahertz is the self resonance frequency for this. Q becomes 0 here, Q has a peak around 2 gigahertz, So this is your window where you are going to get the maximum Q. You see this is your recommended window where you are going to get very good inductor value. What is the value of the inductor Q? Q is 20. Okay, so a Q of 20 is decent, it is a good Q. Higher the Q better it is, but 20 is decent, so you are going to operate there. But if you operate here, for instance, your Q is only 5, that is terrible, and at one point the Q becomes 0, then the Q becomes negative, which means it is a capacitor. And you can see that this is the regime, or this is the regime rather, where metal losses are going to dominate, and that is again the low frequency regime, right. So if I look at the inductance value, on the left side is the inductance value and this is the inductance value. It stays close to 5 nanohenry, maybe around 4 nanohenry. It stays at 5 nanohenry and then it shoots up, okay, to almost 35 nanohenry, and then it suddenly comes down to negative value. This is actually does not mean that the inductance value has increased, it only means that capacitive coupling is going to increase, your Q factor is reducing a lot. So you should not be using this part. This is your part where your inductance is fairly constant, close to 4 to 5 nanohenry, but this is your part where your Q factor is good, so you are going to use it there only. Okay. So as I told you, at higher frequencies your capacitive coupling increases and your current will start flowing in the substrate. Okay. So this frequency, the 5 gigahertz I talked about, here it is, for instance here, which we call the self resonance frequency, it is basically the frequency at which the inductor becomes a capacitor. The capacitive component, because of the coupling between the metal line and the ground plane, dominates over the inductive behavior. Okay. So the inductor will self resonate at that frequency. Alright, so that is what we said. So this is generic for all inductor. Now whenever you have a magnetic field, there are things that you have to take into account. For instance, there is something called eddy current. I am sure you have heard about or studied about eddy current in your 10+2 and undergrad also. Whenever there is a varying magnetic field you are talking about, it will induce an eddy current, or it is like a loop current on the ground plane, okay, and that is induced by the magnetic field, and it is an inductor, of course, you have to remember that. The eddy current will have a direction opposite to the direction of the current flow in the inductor spiral. So if you recall, this is your inductor, maybe I can just remove the annotation here, and if you see there is this current, suppose the current is flowing in this direction, okay. So the current is flowing in this direction, alright. So what will happen is that this magnetic field that varies with time, it will induce this loop current on the ground plane, or what is called eddy current, which will flow opposite to this direction. And whenever the current is flowing in the ground plane opposite in direction to the desired loop current in your inductor, it will basically lead to a reduced inductance, and that is a very undesirable phenomena. So this eddy current is going to create an opposite current on the ground plane, that is not a good thing. Here 10 micron is referring to the thickness of the substrate, and maybe it is a thickness of the epi layer, the silicon or whatever, and this is your substrate. If it is a CMOS, there is going to be a lot of leaky substrate effect If it's a compound semiconductor, this is much more mitigated or reduced, but here from the picture it looks like it is a CMOS or a silicon based thing. Now eddy current is one component that is going to create a headache for us, because the current is going to flow in the opposite direction and to the direction of the current in the spiral, and that is going to reduce the inductance. And secondly, there is also something called substrate current. This is induced by electric field. So there is an electric field also, of course, and that electric field, and there is a ground plane below. The electric field will induce some leakage to the substrate. Okay, the substrate current will flow vertically like this, and it is orthogonal or perpendicular to the direction of the eddy current. The eddy current and the substrate current are basically 90 degree to each other. Eddy current flows in the ground plane, parallel to the top, the surface, whereas the substrate current is flowing vertically, because it's like you can think of it like a leaky capacitor. It's a substrate current that is induced by the electric field, okay, and that's a conducting and in effect, and that's also a pretty bad thing in a way. The compound semiconductor with semi-insulating substrate, this would be much more mitigated or suppressed, okay. So there are many losses in the inductor. I already talked about eddy current and substrate loss, but maybe we can dwell on that a little bit more. So losses can happen in the metallic lines also. They can also happen in the substrate, as I told you, okay, and I told you that at lower frequency metal resistive losses will dominate, so the Q is lower, and once you hit the peak Q, after that your substrate losses will become dominant, which means your capacitive coupling to the substrate will become dominant. That gives you the substrate current, for instance. Now this metal line losses, the resistive losses, you can mitigate them by two ways, or actually quite a few ways, but predominantly you can create several metal layers. Essentially you try to create parallel paths in the metal. You are shunting different metal layers, that is to reduce the DC resistance. If you make your DC resistance lower, you are going to get lower resistive drops. It will help you reduce the metal line losses. So one of the ways is to basically thicken the metal, or you can create several parallel metal layers, or you can shunt several metal layers. But the problem is your peak value of the Q, your self resonance frequency, those values will be affected when you create such shunting of several metal layers. You want to parallelize several metal layers, okay, then that will be a problem, because it will affect your Q. If you use a thicker metal layer, then you have to talk to the foundry. The foundry has a set process. They may not be willing to change their process just to accommodate a thicker metal layer. They have a range of metal thicknesses that they will allow, beyond that may not be viable, okay. Another technique is that people use narrower inner lines. So inner coils. So in inner coil the lines are narrow, and in the outer coils the lines are much wider. This is apparently to reduce again the outer wider lines will basically help you reduce the DC resistance in a way, okay. And there is something called proximity effect. When metal lines are close by each other, they also try to have an effect on one another. It's called proximity effect. So those things can be mitigated, okay. But beyond the DC metal line losses, there is also skin effect that we talked about in I think the last lecture or the last to last lecture, where at RF frequencies the current will tend to aggregate and flow on the periphery of the metal line and not throughout the metal line. So the center of the conductor will not carry current, and that depends on the skin depth, by the way. So because of this skin effect that comes into picture, you will have further resistive drops in the metal, okay, and that is not a good thing. Again, you will have more metal losses, I would say, okay. So these metal losses are modeled as frequency dependent resistance, which is precisely this. We talked about this, the resistance which is in series with the desired inductance. This is in series with the desired inductance. This is the desired inductance, right. So it is in series with desired inductance, and that is how you capture the metal line losses, okay. Now I already talked about eddy current, so I am not going to repeat all the things again. But the way you can mitigate the eddy current is basically the ground plane needs to have a pattern shield. What I mean is by something like this, okay. You can see on the ground plane you can create a pattern like that. The reason you have a very interesting looking pattern is because you want to kind of have this lines perpendicular or orthogonal to the flow of the current direction. That is why you have this leaf like a pattern here, okay. But there are other kinds of pattern also. These white spacings that you see here are actually discontinuity. The metal line is patterned. You can do lithography and you can deposit metal, or you can maybe etch away metal from these white areas, the white lines. So a eddy current that tries to flow, it will see an abrupt discontinuity. There is no metal line. You need a smooth metallic plate for the eddy current to flow. If you have discontinuity like that, then the current cannot flow. If the current wants to flow, there is both sides, there is this gap, this dielectric gap, it cannot flow. So this kind of a pattern ground shield can mitigate eddy current to a significant extent, and you can you can help, you still have a ground plane, but you basically mitigate your eddy current effect. Okay. So the eddy current is there. Now the electric field sets up two components. One is the substrate current, the loss that I already talked about, which is flowing vertically through the oxide, it's like the substrate coupling. There is also a dielectric loss, which we also call displacement current, and typically it can be ignored. A displacement current is like the sudden current, the small current that will flow the moment you change the potential, and in this case there is an oscillating electromagnetic field. So you have a small displacement current that will flow and a proper substrate loss based current that will flow, but typically the displacement current is negligible, so forget about it. Okay, so the substrate loss is very important, and the substrate loss basically, eddy current is a substrate loss, but that is due to magnetic field. What I am talking about, the substrate loss, is the one that is introduced by or induced by the electric field. The electric field can induce this substrate current that is leaking, and that is also not a good thing. So how will you reduce the substrate loss? The way to reduce substrate loss is that you have to reduce the electric coupling between the inductor spiral lines and the substrate. The way to reduce it, of course, you reduce the inductor area. If you have a lower inductor area, it will couple less to the substrate, but that you may not have much of a control, because your inductor area will also be defined, it will also determine the inductor value. Then you can increase the dielectric thickness. I am going to put the inductor metal line on the top much further away. I am going to put this much, instead of 10 micron, I will have it much further away, maybe 20 micron, 100 micron, but that is a process parameter. You may not be able to do that, it will depend on the foundry. Okay. Then you may want a low K dielectric. I will not take silicon nitride, I will take a very new exotic type of a dielectric which has a even lower dielectric constant, and that will reduce the capacitive coupling between the metal line and the substrate. But again, that is a process parameter. The foundry that you are using for fabricating, they may not allow you to use a very exotic or a new dielectric. They will have a set process, you have to stick to that process. Then you can reduce eddy current and potential current by this same thing I told. You have to have narrower inner turns, very narrow inner turns, and then wider outer turns. Okay, wider outer turns. So that will reduce the DC drop, and also that apparently reduces eddy current, because the lower turns inside will try to reduce the eddy current, and the wider turns outside will reduce the DC drop. Okay, but all said and done, RF CMOS process is still a very lossy process for RF, a high quality RF device. Your Q factor is predominantly low, pretty low, your areas are pretty large, and so this kind of passive inductors, etc., are not the best, they cannot be best implemented on a CMOS kind of a platform. This is the reason RF CMOS did not emerge at the same time as compound semiconductor based passives. Later on, there are all these advanced fabrication techniques and all these different nodes with which people tried to do this, but still passives are really challenging to implement on RF CMOS because of the lossy substrate. Okay, I keep telling that again and again. If you have RF SOI, that we talked about, then yes, your substrate coupling can be reduced, and to some extent, and you may be able to get passives which are better than that you get in RF CMOS process. But it is not to say that you don't have passives, you do have passives, but they are just not as good as those on compound semiconductors, okay, because of the nature of the substrate. So this image again, it's a schematic here. Again, it basically gives you a feel of how the electric and the magnetic fields penetrate a silicon, a pure silicon. So I am looking at lower frequency like a few gigahertz. The circular lines are the magnetic lines, always remember that, okay, and the vertical lines, the arrows, are the electric field lines. You can see that electric field lines are barely penetrating the substrate, but the magnetic field lines are penetrating deep in the substrate at lower frequency ranges like a few gigahertz. And when this happens, when electric field are not penetrating much, your dielectric loss is 0, but because magnetic fields are penetrating a lot, your eddy current will be significant. So you have to have a ground shield, a pattern ground shield that we talked about. If you go slightly higher, say X band, maybe 8 to 12 gigahertz, you are talking of an increasing penetration of electric field in the substrate, so that now dielectric losses also start mattering. The magnetic field still continues to penetrate deep, and so your eddy current losses are still there. So you still need a pattern ground shield. You go to few tens of gigahertz to 100 gigahertz, for instance, you are now talking of a quasi TEM mode, almost TEM mode, where electric field penetrates much deep and the magnetic field also penetrates deep, and so your both losses are significant now. And beyond 300 gigahertz, at that range, you are talking about more than millimeter wave, approaching sub terahertz. Your magnetic field does not penetrate the substrate anymore, it's on the top, and so the electric fields penetrate deep in the substrate. and now your eddy current losses are negligible because your magnetic fields are not penetrating deep. However, your dielectric losses are significant. This is just to illustrate how the electromagnetic fields kind of penetrate, what kind of losses matter in silicon as you go from a few gigahertz to few hundred gigahertz. Okay, that is just the point. Now actually when you have an inductor fabricated, no, you need to characterize it. First, when you are doing this, you need to characterize the inductor, you need to model, verify the model against the the characterization results, iteratively improve and get to a robust model and characterize data. Once you have that, then you do not necessarily need to characterize every time. You know the model and you will use that model, okay, as a part of something called PDK, process design kit. It's a different thing, I'll come to that later if time permits. You use the model as a part of process design kit, which you can give to a designer, a circuit designer. The foundry will give it to the circuit designer, and the circuit designer will use that to design an inductor within a certain range. He or she will be free to choose the number of spiral turns or some of the dimension of the inductor line, 3 turn, 3.5 turn, 4 turns inductor, etc. He or she can choose those, and the model will predict what kind of inductance are you going to get, what kind of quality factor you are going to get, because already you have done a thorough or comprehensive characterization and modeling of these inductors on the test runs that you do before you release the model to the designer, the circuit designer. So for instance, in this image you see that this is an actual inductor on a substrate, and this is the ground signal ground, the GSG configuration, the ground signal ground configuration on which you are going to bring these RF probe tips on wafer for instance, and you are going to characterize the S parameter of the inductor, S11, S21, S12, S22. You are going to characterize the S parameter. You will plot the S parameter with respect to frequency. In the meantime, you will also develop model. The designer will develop the model based on the dielectric thickness, because based on the dielectric constant of the epi layer or the dielectric below, the dimensions of the inductor spirals, etc., etc. He or she will design them, come up with the model, and the model will predict these S parameters. Then you experimentally measure them based on the same dimensions that you are using. The dielectric thicknesses, the dielectric constant, everything have to be same between the model and the experiment. Then you experimentally measure them and you overlay. You overlay the modeled S parameters with the experimental S parameters, and you see how close or far you are from the experimental parameters. Okay, so that's how you develop. So this is just to show that this is how the actual on wafer fabricated. This is probably an image from the file, but this could also be an image from an actual fabricated die, that you need an inductor and you are going to measure on wafer probes. You will do an on wafer probe measurement of the S parameter on an inductor. Okay. So CMOS inductor, for instance, this is again, if I talk about CMOS inductor, the Q factors are not as great, but yeah, I want to highlight a few things here. This image is not of much novelty, you have already discussed this. Low frequency, you have metal lines dominate, high frequency capacitive couplings dominate. This is the peak, so this is your desired, your Q factor is only 10, it's pretty low. Okay, your Q factor is pretty 10. Some values I am taking, say 3.5 micron thickness of the epi, and the metal line could be 1.7 micron probably. I don't know what T represents here, but depending on the different dimension, you are going to model and find out the Q factors and the inductance values that you are going to get, and you experimentally measure them. Okay. What is very important in these two plots is to highlight the effect of capacitive coupling and the resistive losses separately. So in this plot that you see, we are plotting the Q factor as a function of frequency, where I am only changing the capacitive coupling to the substrate. So I have the oxide thickness, where I am going to change the capacitive coupling. Maybe I have different thicknesses of oxide. So this line corresponds to 1/4 of Cox, suppose. Some Cox I am taking, some oxide value, capacitance value. If I take 1/4, I get that. If I give half, I get that. If I exactly take Cox, I get that. And if I take 2 times that, then I get that. What do I see? I see that the Q factor is reducing dramatically as I am increasing the capacitance value in the high frequency regime, which is precisely what I have been talking about. Interestingly, in the lower frequency regime, the Q factor stays the constant, does not depend on this capacitance value. The value of Q factor is constant. Why? Because the metal line is the same. So metal resistive losses are same, so the capacitance does not play a role in the low frequency. Conversely, if I keep the capacitance same, say Cox, but I keep changing the metal line sheet resistance, maybe I make the metal thicker or things like that. So then I see that if I have a higher metal resistance, I get this 2Rs, this is Rs, this is half of Rs, this is 1/4 of Rs. I see that the higher frequency part does not change, you see they are all constant. The metal resistance does not affect the high frequency Q factor of an inductor, but the low frequency Q factor of the inductor is dramatically changing as you are changing the metal resistance. With higher metal resistance, the Q factor keeps coming down. So with a lower metal resistance, your Q factor will improve, but this improvement is in the lower frequency regime only. At higher frequency regime, it is capacitance alone that matters. So this is a very important understanding that you need to have in terms of inductor. Okay. So the last thing is basically that I told you about the on-wafer characterization, how you can build an equivalent model. The characterization and modeling have to go hand in hand. Simulators are used. HFSS is a simulator to do the electromagnetic field simulation. People also do ADS. ADS also has an electromagnetic field simulation component, if I am not wrong. Okay. So then you can predict the Q factor, the inductance value, etc., and you compare with the fabricated values. Okay. Typically you try to maximize the Q value. CMOS will always suffer from the lossy substrate, cannot help it. This is the destructive coupling I talked about in the beginning of the lecture probably, but you try to minimize that by keeping this far away. Okay. Now here is the important thing. Q factor can be improved by either an infinitely resistive substrate such as a gallium arsenide substrate, for instance, a compound semiconductor. If you have an infinitely resistive substrate, then no current can flow, or you have a completely metallic substrate where no voltage can drop. In a metallic substrate you cannot have any voltage drop. In that case also Q factor can improve, but a metallic substrate will lead to this the eddy current and capacitive couplings will increase. So if you bring it too close, so those things also need to be taken care of. Okay, and I already talked about the pattern shield, so I will not talk about that. The last slide on the inductor is to basically give you some numbers of state of the art inductors using different technology. So RF CMOS, for instance, your Q factors are typically 19, 20 at a frequency range of 10 to 30 gigahertz. Now if you talk about SOI, it is improved, no? You get a Q factor of 27 at 2 gigahertz, for instance. You may give even at slightly higher frequency, you will get the same. Okay. VLSI CMOS is even worse. You get a Q factor of only 10 at 5 or 10 gigahertz. It is much worse than RF CMOS. Okay. Gallium arsenide gives you 31.6 and MEMS gives you 36 Q factor at these frequencies. MEMS is basically you have like a cantilever, you can fabricate suspended structure. So that is a different thing we are not going to talk about at all here, but gallium arsenide gives you 31, which is very high at 30 gigahertz. Okay. And you look at the self resonance frequency at gallium arsenide, your self resonance frequency is 82.6 gigahertz. This is a representative number. It means up to this frequency your inductor is an inductor, whereas for RF CMOS you see 64 gigahertz. SOI maybe 100 gigahertz because it is very insulating. VLSI even lower. MEMS has this disadvantage, it cannot go to super high frequency. Okay. These are inductor values, 2.7 nanohenry, 0.5 nanohenry, excuse me, etc. These are different nanohenry values are there. So that brings us to a conclusion of this lecture and the discussion on inductor. We started from the definition of what fundamentally inductor does. It stores magnetic energy. A simple line will do that with a ground plane, but a spiral helps improve the real estate, the footprint. You can decrease the footprint, get more inductance. Okay. We talked about self resonance frequencies, we talked about the losses, different kinds of losses that can happen in an inductor, and finally we showed some representative values of inductance and Q factors from contemporary technologies. Okay. So I hope we are able to get a good feel of what inductors are and how the different aspects of inductor in respect to the passive. So going ahead in the next lecture we are going to look at some more passive technologies that are used in RF circuits. Okay. So thank you for your time.